We live in a world of three spatial dimensions: up, down, left, right, forward, backward, plus time. But what if that's not the whole story? String theory, one of the most mind-bending ideas in all of physics, proposes that our universe actually has extra hidden dimensions all around us, curled up so small we can't see them. So the big question is, where are they, and what do they do?
This is without a doubt one of the biggest mysteries in modern physics. The answer involves an idea that is both beautiful and deeply strange. So let's take a journey into these hidden dimensions and see how the simple fact that strings are, well, strings, and not points, completely changes the rules of reality.
Here's our roadmap. First, we'll cover the basic idea of how you can even hide a dimension in the first place. Then we'll see what happens when you put a string in there. That will lead us to a truly bizarre duality, show us how geometry itself can create new forces, and finally, we'll take a peek at some even wilder shapes.
All right, to get a handle on how string theory tucks away its extra dimensions, we actually have to rewind the clock about 100 years to an idea that laid all the groundwork for what was to come.
This central idea is called compactification. It's actually pretty simple. What if those extra dimensions aren't huge and infinite like the ones we know? What if, instead, they're curled up into an impossibly tiny loop, so small that we've just never noticed them?
You've probably heard this one, but it's the perfect analogy: a garden hose. If you're looking at it from really far away, it just looks like a one-dimensional line. But imagine you're a tiny ant on that hose. For you, there are two ways to move. You can walk along the length of the hose, or you can walk around it. That circular dimension was always there. It was just hidden by distance.
Now, here's where it gets really cool. The Kaluza-Klein mechanism tells us that a particle moving around that tiny hidden circle has energy, it has momentum. But from our perspective, in our big dimensions, we can't see that little loop-the-loop motion. So where does that energy go? Well, thanks to our old friend E = mc², that unseen energy of motion shows up to us as mass. The faster a particle zips around the hidden circle, the heavier it appears in our world, creating a whole tower of particles with ever-increasing masses.
Okay, so that Kaluza-Klein idea is great for point particles. But string theory? Well, the clue is in the name. It's not about points. It's about tiny, vibrating strings. And this one little change, it blows everything wide open. Let's see how.
So what's the big deal? What can a string do inside one of these curled-up dimensions that a simple point just can't? The answer introduces a totally new feature of reality, something impossible in a world of point particles.
A point particle can only move. It has momentum as it zips around that circle. A string, because it's an actual loop with physical length, can do that too. But it can also do something completely different. It can literally wrap itself around the entire dimension.
We call this winding. A closed string can loop itself around the dimensions once, twice, 100 times, any whole number really, and that number, how many times it's wrapped, becomes a new quantum property. We call it the winding number, and it's a physical state that's just completely impossible for a zero-dimensional point.
So this is the absolute key idea to get. A string in a compact dimension now has two ways to hold energy. You've got the momentum mode, which is energy for moving around the circle, and now you've got this new winding mode, which is potential energy from being physically stretched around the circle. Moving versus stretching. Remember that, because it's about to get weird.
And now that we have those two kinds of energy, momentum and winding, we're ready for one of the most famous, most bizarre, and most profound results in all of string theory. This is the part where our everyday intuition about size and distance completely breaks down.
Let's do a little thought experiment. We take our circular dimension and we start to shrink it. What happens to the energy cost of those momentum modes and those winding modes?
Okay, don't worry about the math here. Just look at the idea behind the equation. The total energy has two parts. You see the part with n divided by r? That's momentum. As the radius r gets smaller, that number gets huge. It gets harder and harder to move. Now look at the other part, with w times r. That's the winding energy. It does the exact opposite. As r gets smaller, that part of the energy gets smaller. It's a perfect tug-of-war.
This table makes it crystal clear. In a big, wide circle, it's really easy to move around. That's a low energy cost. But stretching a string around a huge circle takes a ton of energy. Now, let's shrink that circle way down. Suddenly, it's really hard to squeeze in there and move. High energy cost. But wrapping a string around a tiny little loop, that's super easy. The costs just completely flip.
And this leads us to the absolutely stunning conclusion of T-duality.
It means that the physics in a universe with a large radius r is identical, completely indistinguishable from the physics in a universe with a tiny radius. The winding modes in one universe exactly mimic the momentum modes in the other, and vice versa. You literally cannot perform an experiment to tell the difference. This suggests there might be a fundamental minimum length in the universe, a point where getting smaller is actually the same thing as getting bigger. Wow.
So this T-duality thing isn't just a weird mathematical trick. It has profound physical consequences. Let's move on and see how this leads to something even more incredible. The idea that new forces of nature can be created directly from the geometry of space.
So get this, there's a magic point, a special size for this circle called the self-dual radius. It's that perfect sweet spot where the energy it costs to move around the circle is exactly the same as the energy it costs to wrap around it. And at that precise radius, something amazing happens. Certain string states that would normally be very heavy, very massive, suddenly become massless.
You don't have to follow the equations here, just appreciate that they are the proof. They show, definitively, that at this one specific geometric point, new massless particles just pop into existence in the theory. And in physics, what do massless particles mean? They mean new long-range forces. The actual shape of space is giving birth to fundamental forces of nature.
Physicists call this phenomenon symmetry enhancement. At any random size, the rules of the game are pretty simple. But when you tune the radius to that one special value, bam, the theory gains new, more powerful rules. It blossoms into the kind of complex, beautiful symmetries that actually govern forces we know, like the weak nuclear force. The geometry itself is telling the universe how to behave.
So far, we've only been talking about a simple, perfect circle. But these hidden dimensions can have much, much more complicated shapes. So for our last section, let's take a quick look at one of the next steps on this crazy journey.
We can create shapes called orbifolds. A good way to think about it is like taking a flat piece of paper, folding it in a specific way, and then gluing some of the edges together. This process can create points that aren't smooth. They're sharp, like the tip of a cone. Now, in traditional physics, these singularities are a complete catastrophe. All the laws of physics just break down.
But here's the thing. String theory is not bothered by these sharp corners at all. A point particle would get stuck and fall into that singularity and the physics would go haywire. But a string is a little loop. It's extended. It can pass right over that sharp point without ever touching the singularity itself. It inherently smooths out the geometry, which just hints at how powerful this framework really is.
And that leaves us with one final, tantalizing thought. We've seen that the absolute simplest possible hidden dimension, a single circle, already gives us this mind-bending duality between big and small, and can literally create new forces out of pure geometry. So it really makes you wonder, what other incredible physics, what other fundamental secrets of our universe are hiding out there in the complex, twisted-up shapes of dimensions we can't yet see?